Hi, I'm Pavas Chopra, and today I'm going to present my work for the pattern recognition course. The project that I worked on was automatic lung cancer detection using deep residual networks. So basically, lung cancer is the leading cause of death among both the genders. A lot of money, a lot of research is being done, a lot of money is spent in treating it. And despite the very serious nature of the disease, if lung cancer is detected early, it can be cured. So, the main motivation of this project is to develop an automatic medical image analysis system that can predict in a very fast manner whether the lung scans given to the system have lung cancer or not. Most of the lung cancer images are basically obtained using CT scans, and in this project we are going to use a data set which is hosted on Kaggle that has over 1,000 lung scans, and we will try to develop an algorithm that can classify these lung scans as cancerous or not cancerous with a reduced number of false positives and in a fast manner, so that we can tell patients at an early stage that they have lung cancer and that they have better chances of survival. So over the years, there has been a lot of related work in this field. Researchers have used deep neural networks in a lot of similar fields. For example, detecting brain lesions or detecting skin lesions, or using CNNs to actually find nodules in the lungs and classify them as cancerous or not cancerous. So, if you see over the years, there has been increased research in medical image analysis combined with the use of deep learning methods. The algo that we follow is as follows. We first do pre-processing of all the lung scans in order to remove noise and infer all the data that is missing from these scans. So the first step is we load these DICOM files, which consist of multiple slices per subject. We load these in a Python list and we add all the missing data by inferring it based on the already existing data. Then there is a unit of measure called the Hounsfield unit, which basically measures the radio density of each CT scan. So we convert all the raw pixel values to this unit called the Hounsfield unit. Then we notice that all the slices within a subject and even across subjects have different spacing, have different distances with respect to each other. And so in order to overcome that, we perform resampling so that we can standardize this distance between all the slices across all the subjects. Then we apply a lung segmentation mask and perform lung segmentation. After that, we basically crop out all the unnecessary regions, all the white space in the image, and we resize all the lung scans to a constant size of 512 cross 512. So here on the left, we can see an example CT scan when loaded from the DICOM file, and on the right is the lung after we apply the lung segmentation mask. The second step that we perform in 2 of the 3 experiments is averaging. So the motivation behind averaging is that each subject has a variable number of slices, and what we want is we want to ideally standardize the number of slices per subject. So we perform 2 kinds of averaging. In the first kind, what we do is for a particular subject, we average over all the slices in that subject. So for every pixel, we basically average across all the slices for that subject, in the end we get a resultant one slice per subject, which has the same label as the subject label. So for every subject we will get one slice of size 512 cross 512. In the second kind of averaging, what we do is we divide the subject into 100 groups consecutively, and we perform the averaging within these 100 groups, so that in the end we basically get 100 slices per subject for all the subjects. So now what we get is we basically get a 3D structure of size 512 cross 512 cross 100. So here the length and width of each slice is 512, and there are 100 slices per subject across all subjects. We will feed this 3D structure into a deep residual network that has 100 channels. Next, we have used deep learning to train the model for this problem statement. The motivation behind using deep neural networks is that they have the ability to basically learn features automatically, learn high level features automatically when we give them as input huge amounts of training data. And more often than not, it has been observed that these automatically learned features, they work better, they perform well as compared to the traditional approach of using handcrafted features. Also, with the availability of powerful computing resources and GPUs, we can highly parallelize the training and testing of these deep neural networks, which basically speeds up the whole experiment and gives faster results. So in this project, we have used the Keras API on top of Theano to build our deep neural network. The deep neural network that we have used in this project is basically the deep residual networks, or the ResNets. This was the state-of-the-art neural network architecture as of May or June 2016. The motivation behind coming up with a ResNet was that if you take a shallow model and if you add more layers to this model using identity mappings, you should ideally expect a training error that is less than or equal to the original shallow model, because all we've done is we've added more layers, but we've added more layers using identity mappings. So the training error shouldn't ideally decrease, but empirically experiments show that the training error increases on adding these identity mappings, or when we add more number of layers, the training error increases, which should not be the case. So therefore, researchers came up with the ResNet architecture. So here on the left, we can see a plain neural network. So here, for example, if we're taking 2 layers, for instance, so HX is basically the desired mapping that we want to fit by these 2 layers, these 2 weight layers, these 2 stacked layers. So this is a plain stacked neural network. On the right, what we see is a ResNet in which basically, given these 2 weight layers, we want to fit a function fx as compared to the function hx in the left figure. We want these 2 layers to fit the function fx, and what we do is we add an identity mapping from the input to the output of this residual block. So this basically gives us the equation where hx is equal to fx plus x. So here the function fx is called the residual mapping with respect to the identity shortcut connection that we've added from the input to the output. So basically this is For example, the architecture of the residual network. Um, we can basically convert any plain regular neural network to a residual network by adding identity shortcut mappings in this way. The basic model of all residual networks basically have convolutional layers of size 3 cross 3. In every iteration, their spatial size is decreased by half and the number of filters is doubled. All ResNets are trained from scratch and they use batch normalization. They don't have fully connected layers at the end of the network. So in this project, we're going to use an 18-layer ResNet to learn 3 models for 3 kinds of experiments that we've performed. And these experiments have been performed by doing the pre-processing and averaging techniques that we discussed before. So the data set is basically hosted on Kaggle. It has over 1,000 CT scans of lungs, and this data set is provided by the National Cancer Institute. This has many low-dose CT scans images, and these images are stored in the DICOM format. Each image has a variable number of 2D slices. There are a total of 1,397 subjects in this data set, out of which 362 of them have lung cancer. That means there are about 362 positive samples, and majority of the data set has negative samples. Now we will talk about the experiments that we performed. So the problem statement that we're working on is a relatively new problem statement. So we tried to experiment with a lot of new techniques, different kinds of techniques, to find out which worked the best for this kind of a data set. So we basically performed 3 kinds of experiments. The first experiment, experiment A, basically involved training a ResNet with dynamic batch sizes. Basically for this data set, the labels, the ground truth labels that have been provided to us, these labels have been provided per subject. For example, a subject has been classified as either 1 if they have lung cancer, or they have been classified as 0 if they don't have lung cancer. The issue with this is that each subject has variable number of slices, and what we ideally want is labels for each slice. So what we do is, for this experiment, we basically decompose all these subject level labels to slice level labels. We do this by basically assigning all the slices of a subject with label 1 as 1, and all the slices of a subject with label 0 as 0. So after doing this, we perform the basic pre-processing techniques that we've discussed before, and we train a residual network with dynamic batch size. So the dynamic batch size is basically determined by the number of slices that each subject has. So this ensures that the ResNet is looking at the data of just one subject in one batch and not mixing the data of one subject with another subject. We have trained this ResNet for 100 epochs. In the second experiment, experiment B, what we do is we do the basic pre-processing as discussed before, and we do the first kind of averaging. That is, we take all the slices in a particular subject and we average all the values for each pixel to give us a resultant slice per subject. So that means for every subject we will have just one slice of size 512 cross 512, and this slice will have the same label as the subject label, and we have used these slices to train an 18-layer ResNet with a constant batch size of size 20, and we have again trained this ResNet for 100 epochs. In the third experiment, we have again performed the basic pre-processing technique as discussed before, but the averaging that we've done here is the second kind of averaging that we discussed before. So basically here we've divided each subject into 100 groups and averaged within each group to get a 3D structure with 100 slices per subject. And we have input all these structures into a ResNet with 100 channels. And again, we have used a constant batch size of size 20, and we have trained this ResNet for 20 epochs. So we have done the performance evaluation by calculating the prediction accuracy based on the models that we've trained for each of the experiments, and also by calculating the log loss based on the probabilities that the models give us for each of the experiments. So the log loss is given by the equation as shown in the slide. Here n is the number of patients in the test set, and yi cap is the probability that the model predicts, and yi is the true diagnosis, that is, it's the true label that whether that subject has cancer or not. So these are the results that we got for each of the experiments. Experiment A gave us an accuracy of 68% with a log loss of 1.62. Experiment B gave us an accuracy of 70% with a log loss of 1.54. And experiment C gave us an accuracy of about 59% with a log loss of 1.74. We can see that the accuracies are not very high, they're relatively low, while the log losses are high. This is probably because the data set was extremely biased towards negative samples, as there were very few positive samples, and even the very few positive samples that were there, they were of extremely low resolution, they were extremely noisy. Apart from this, the decomposition of each of the subject level labels to the slice level labels also introduced errors, and we do need to come up with a better way to do this in the future. So the challenges that we faced in this project was, as we mentioned before, the data set is heavily biased towards negative samples. Apart from that, the data set has extremely low resolution CT scans. Despite the pre-processing that we did, the data is still noisy, the data still consists of holes, and we still need to figure out better ways of doing pre-processing for this data. Then each subject has a variable number of slices, and we were not able to figure out a very good way to basically standardize these number of slices per subject. This is again something that we need to work on in the future. Apart from that, the decomposition of the subject level labels to the slice level labels required a lot of assumptions, and these assumptions tend to introduce errors in the model that we trained. So this was another challenge that we faced. The last challenge was that the data set was huge, the number of subjects was huge, and the CT scans were a lot, and we require powerful computing resources to be able to train a deep-led ResNet on a data set that is this huge, and we do not have such powerful computing resources at this time. So as part of the future work, what we would ideally like to do is we would like to clean up the data set, figure out better pre-processing techniques, use better denoising techniques, or better image enhancement techniques to basically clean up the data set and pre-process the images in a better way. The second thing that we would like to do is come up with better ways to decompose subject level labels to slice level labels. One possible method of doing this is by using the Luna 16 dataset. So the Luna 16 dataset has labels on the slice level, and it tells whether a particular slice contains nodules or not. So what we could do, for example, is train a CNN on the Luna 16 dataset and then the run our data set as use our data set as the testing set, and get the slice level predictions from this pre-trained Luna 16 dataset model. Once we do get our slice level labels, we can then perform our experiments as usual. We would also like to train with different kinds of CNN architectures and explore more 3D convolutional neural nets in the future. So, to summarize and conclude, what we did was in this project, we basically tried to classify lung scans as cancerous or non cancerous, and we were trying to do this automatically using pre-trained models, so that we can get faster predictions. So the first step that we did was we pre-processed the data. After pre-processing, we performed some kind of averaging techniques on the data to get a consistent number of slices per subject. We performed 3 experiments. We trained or learned 3 kinds of models on the data set that was hosted on Kaggle. And we used deep residual networks for all of these 3 experiments. The size of the deep residual networks was 18 layers, and we calculated the accuracy and log loss for each of these experiments. What we noticed was that the performance of all the 3 models was relatively low, not as expected, and this was because of the various challenges that we faced in the project, and some of them we did discuss before, and we would like to work on this in the future and come up with techniques that do increase the accuracy. Now we're going to show a short demo. So here, this is basically a testing file that we've made. This file opens up, loads already pre-trained model for experiment B, in which we performed averaging to get 1 slice per subject by basically averaging over all the slices in a particular subject. So we're loading this pre-trained model here, and we're testing this pre-trained model on about 15 to 20 samples, and the program here will basically give us an accuracy and a log loss for these 15 to 20 samples. The program basically here, so the log loss is about 1.11, and the accuracy for these 15 to 20 samples is 66.67%. Thank you.